In this video, I'm going to talk about real numbers and the concept of greater than and less than. And I'm going to do this by illustrating using a number line. Now, a number line, I'm sure you've seen these before, looks like this. It's basically a line with arrows on each end, and it's divided in the middle by 0. And so this number line contains all real numbers. One of the definitions of a real number is any number that can appear on a standard number line. So you have 0 in the middle, and normally what you see is tick marks for the whole numbers going up from 0 and going down from 0. Now you'll notice that on both ends you've got an arrow which tells you that the number line extends forever in both directions. So if you go all the way to the right, you'll keep going up to positive infinity. And if you keep going to the left forever, you'll go down to negative infinity. And so this is a basic number line. Divided in half by 0. Anything that is to the right of 0 is a positive number, and anything that's to the left of 0 is a negative number. Now this brings up the concept of greater than and less than. Now the number line makes it very easy to see what is greater than or less than another number. If we use 0 as our reference point, anything that's to the right of 0 is greater than 0, and that's how we classify the positive numbers. Anything to the left of 0 is less than 0, and so that's how we classify the negative numbers. Now you can use other numbers than 0 as your reference point for greater than or less than. For instance, we can arbitrarily decide that we're going to use 3 as our reference point. And so anything that appears on the number line to the right of 3 is greater than 3. Anything that appears to the left is less than 3. So we can say that 4 is greater than 3, or that 2 is less than 3. Now, as I was saying, we mark tick marks for the whole numbers, but there are numbers that exist between these. So you might have numbers like 1.3. 1.3 would be on the number line right here. We don't mark it, but it's there. In addition to decimals, we can also have fractions on here. You might have 3/4, and that would be right about here on the number line. Or you might even have numbers like square roots. So say the square root of 5 would be on the number line about right here. And so you have all these different types of numbers that appear on the number line, and they're all real numbers. And so the number line is just a handy way to be able to graphically represent the whole spectrum of real numbers.
Factors. Factors are numbers that are multiplied together to obtain a product. For instance, in 2 times 3 equals 6, 2 and 3 are the factors. Common factor, a number that divides exactly into 2 or more other numbers. For example, the factors of 12 are 1 times 12, 2 times 6, and 3 times 4. So the factors of 12 are 1, 2, 3, 4, 6, and 12. The factors of 15 are 1 times 15 and 3 times 5. So the factors of 15 are 1, 3, 5, and 15. The common factors are 1 and 3. Those are the factors they have in common. Prime number. Prime numbers have two distinct, which means different, factors. 1 and itself. The very first prime number is 2. Because the only numbers, the only factors of 2 are 1 and 2. 1 times 2 is 2. Some people think that 1 would be the first prime number. But 1 only has one factor. 1. 1 times 1 is 1. So 1 is commonly thought of as neither prime nor composite. A composite number being a number that has more than 2 factors. So 2 would be the first prime number, then 3, because 3 has only 2 factors. 1 times 3 is 3. 4 would be composite, since 1 times 4 is 4, and also 2 times 2 is 4. 5 would be prime. Its only factors are 1 and 5. 6 would be composite. 1 times 6 is 6, and 2 times 3 is 6. 7 would be prime, since its only factors are 1 and 7. 8 would be composite. 1 times 8 is 8, 2 times 4 is 8. 9 would also be composite. 1 times 9 is 9, 3 times 3 is 9. 10 would also be composite. 1 times 10 is 10, 2 times 5 is 10. 11 would be prime. 1 times 11 is 11. And so on and so forth. There are an infinite number of primes. A prime factor is a factor that's prime. So in our example above, in 12 and 15, the prime factor of 12 would be 2 and 3, and the prime factors of 15 would be 3 and 5. You can also do prime factorization. The prime factorization of a number, for instance, the prime factorization of 12 would be 2 times 2 times 3. That's where you write the product of a number only using primes. And the prime factorization of 15 would be 3 times 5. Unlike just writing the factors of a number, with prime factorization, you use only prime numbers as factors to multiply to get the result of the product you are seeking. Fractions. A fraction is a number that is expressed as one integer written above another integer with a dividing line between them, like x divided by y. So for example, 3/4. In this fraction, 3/4, the top number is called the numerator, and the bottom number is called the denominator. The numerator is the part that's being considered, while the denominator is the whole. So in this fraction, 3/4, we could take a pie shape and cut it into 4 pieces. That's our whole. And the part that's being considered is 3/4. So 1, 2, 3. So now you can see how much of our pie we're talking about, 3/4. We can manipulate fractions, and we do this by multiplying or dividing both the numerator and the denominator by the same number, not by adding and subtracting. We manipulate fractions to do many things. One thing is to compare them. If we were to compare 3/4 and 2/3, we would first need to find what's called a common denominator. Because in order to compare them, I need them to have the same denominator. So I can tell which one's bigger or if they're equal. So we'll take 3/4 and 2/3, and we're going to find a common denominator. When you do that, you want to look for multiples of the denominators. And the least common multiple will be the least common denominator. So the multiples of 4 and 3, 4 is 4, 8, 12, 16, etc. 3 is 3, 6, 9, 12, 15, 18, etc. So the least common multiple between 4 and 3 is 12. So that means I want to change this fraction to something over 12. Same with my other fraction. What I'm doing is creating an equivalent fraction. 3/4 is equal to something over 12. So I'm going to multiply my numerator and my denominator both by 3 to achieve that denominator of 12. So 3 times 3 is 9. And so our fraction is 9/12. And then for 2/3, we'll do a similar thing. We want to change our denominator from 3 to 12. So we multiply 3 times 4 to get 12. And we must do the same to our numerator. 2 times 4 is 8. So now we can easily see which fraction is larger. 3/4 is equivalent to or equal to 9/12, and 2/3 is equal to 8/12. Well, 9 out of 12 is definitely more than 8 out of 12. So we could say that this fraction 3/4 is bigger than this fraction 2/3 if we were to compare them. So let's talk a little bit more about equivalent fractions. All of these fractions are equivalent fractions because they all represent the same value. 2/10, 3/15, 4/20, 5/25. And we could see that they represent the same value more easily by simplifying our fractions. So we said we can manipulate fractions by multiplying the numerator and denominator by the same value, or we can manipulate them by dividing the numerator and denominator by the same value. So if we wanted to simplify this fraction 2/10, we would just divide the numerator and the denominator by the same value. Both 2 and 10 are divisible by 2. So we divide our numerator by 2 and our denominator by 2. 2 divided by 2 is 1. 10 divided by 2 is 5. We do the same thing to our next fraction. 3 and 15 are both divisible by 3. So we divide our numerator by 3 and our denominator by 3. 3 divided by 3 is 1. 15 divided by 3 is 5. 4/20. Our numerator and denominator are both divisible by 4. So divide by 4, divide by 4. 4 divided by 4 is 1. And 20 divided by 4 is 5. Finally, 5/25. Numerator and denominator are both divisible by 5. 5 divided by 5 is 1. And 25 divided by 5 is 5. So as you can see, all 4 of these fractions are equal to 1/5. 1/5 is the simplest form of these fractions, and they are all equivalent fractions since they all have the same value, 1/5. Volume and surface area of a cube. Volume is the space that a figure occupies. So to find the volume of a cube, you just cube the length of one side. A cube is made up of 6 congruent squares. which means all the dimensions of the cube are the same. So instead of length, width, and height, everything's just s. It's all just a side because all the sides are the same. When you multiply side times side, that's side squared, an area of the base, and then multiply that times side again, or the height of the cube. Side squared times side is side cubed, and that gets you the volume. To find the surface area of a cube is made up of 6 squares. Surface area is the area of all the surfaces. And since all the squares are congruent, the area of one square would just be side squared. And there are 6 of those that are all exactly the same. So 6 times side squared. Let's look at an example. Find the volume and the surface area of the following cube. Volume, we start with our formula. Volume is side cubed. And we only need one dimension since they're all the same. We have it, 4 inches. So we substitute 4 inches for our side and cube it. 4 cubed, 4 times 4 is 16. 16 times 4 is 64. Inches cubed is inches cubed. So the volume is 64 inches cubed. Now for surface area. Surface area is 6 times side squared. Side squared gives us the area of one of the square faces, and there are 6 of them, so we multiply it times 6. So the surface area is 6 times, again our side is 4 inches squared. Following our order of operations, we're going to square 4 inches first. So the surface area is 6 times 4 inches squared. 4 squared is 16. Inches squared is inches squared. And then 6 times 16 inches squared is 96 inches squared. So that's our surface area. Volume and surface area of a sphere. Volume is the space that a figure occupies. The volume of a sphere is found by multiplying 4/3 times pi times the radius cubed. The radius is a segment that goes from the center of the sphere to a point on the outside of the sphere. Surface area is the area of the complete surface of the sphere, and it's found by multiplying 4 times pi times radius squared. Let's look at an example. Find the volume and the surface area of the following sphere in terms of pi and to the nearest whole number. We'll start with volume. So first we'll write our formula for volume, which is 4/3 times pi times radius cubed. And then we'll substitute our radius, which is given here as 6 feet. Volume is 4/3 times pi times 6 feet cubed. So the volume is 4/3 times pi times 6 feet cubed. 6 times 6 is 36. Times 6 is 216 feet cubed. 4/3 of 216 is 288. So the volume is 288 pi feet cubed. That's our answer in terms of pi. To find it to the nearest whole number, simply multiply times pi. And 288 times pi is 905 feet cubed. Now to find our surface area. The surface area is found by multiplying 4 times pi times radius squared. So now we need to simplify or substitute 6 feet for our radius. So 4 pi times our radius is 6 feet squared. We follow PEMDAS, we need to do 6 feet squared first. 6 feet squared is 36 feet squared, so 4 times pi times 36 feet squared. And then 4 times 36 feet squared is 144 times pi, 144 pi feet squared. So that's our answer in terms of pi. And then to find it to the nearest whole number, we need to multiply times pi, which gives us 452 feet squared. Absolute value. Absolute value is the distance of a number from 0 and is always positive. It's denoted by a pair of vertical lines surrounding the value, such as the absolute value of 3. You can think of absolute value like you're being asked a question. And the question is, how far is 3 from 0? 3 is 1, 2, 3 places from 0. So the absolute value of 3 is 3. The absolute value of a negative number and its positive counterpart are the same. So the absolute value of negative 3 is also 3 because negative 3 is also 3 places from 0. 1, 2, 3 places from 0. The absolute value of a difference, when you're doing that, the order doesn't matter. Let's look at the absolute value of a couple of differences. The absolute value of 8 minus 3 and the absolute value of 3 minus 8. When you're doing the absolute value of a difference, again, the order doesn't matter. The result will still be the same. Let's see how that happens. Start on the inside finding your difference. 8 minus 3 is 5. So we have the absolute value of 5. And again, absolute value is the distance from 0. 5 is 5 places from 0. Now we'll look at the difference switched around. 3 minus 8. 3 minus 8, you could add the inverse, so 3 plus a negative 8. 3 plus a negative 8 is negative 5, so we have the absolute value of negative 5. And like we talked about over here, the absolute value of a number and its negative counterpart are the same. So the absolute value of 5 and negative 5 is the same because, again, absolute value is the distance from 0, and distance can never be negative. So the absolute value of negative 5 is also 5, since negative 5 is 5 places from 0. Adding and subtracting decimals. When adding and subtracting decimals, first, line up the decimals. We have 4 and 23 hundredths plus 9 and 75 thousandths. Same with subtraction. 5 and 629 thousandths minus 45 hundredths. Then if you have any empty spaces, you can fill in with zeros. Adding zeros to the back of your number, to the back of a decimal, doesn't change the value of your number. So these numbers are still what they were. They're still equal. And then we just add or subtract like we usually would. 0 plus 5 is 5. 3 plus 7 is 10. So write your 0, carry your 1. 1 plus 2 is 3, plus 0 is 3. Bring that decimal down. 4 plus 9 is 13. So our answer, or our sum, is 13 and 305 thousandths. Now for subtraction. We're going to do the same thing, except now we're subtracting. 9 minus 0 is 9. 2 minus 5. We can't take 5 from 2, so we need to borrow from our 6, just like we usually would, and add a 1 onto our 2, which makes 12. 12 minus 5 is 7. And then 5 minus 4 is 1. We bring our decimal down. And 5 minus 0 is 5. So our result, or our difference, is 5 and 179 thousandths.
The processes for converting decimal numbers to fractions and percentages are both fairly simple, so I'll demonstrate both on each of these examples here. First, we have 0.35. To convert 0.35 to a fraction, we'll write the 2 digits in here as the numerator, and we'll take a look at the rightmost digit. The rightmost digit is 2 decimal places to the right of the decimal, so we're going to write 2 zeros in the denominator. So we have 35 over 100. And this can be reduced by dividing both the top and the bottom by 5. 35 over 5 is 7. 100 over 5 is 20. So this is equal to 7 over 20. To convert a decimal to a percentage, all we have to do is move the decimal point 2 places to the right. So 0.35 is equal to 35%. In the second example, we have 0.215. Once again, we'll write 215 as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will write 3 zeros in our denominator. 215 over 1,000. We can divide top and bottom by 5. So 215 over 5 is equal to 43, and 1,000 over 5 is equal to 200. So this fraction is the same as 43 over 200. To convert to a percentage, we can just move the decimal point 2 places to the right. So 0.215 is equal to 21.5%. In this final example, we have 0.842. We will once again write these digits as our numerator. The rightmost digit is 3 places to the right of the decimal, so we will once again have 3 zeros in our denominator. 842 over 1,000. We can reduce by dividing top and bottom by 2. 842 over 2 is 421, and 1,000 over 2 is 500. So this fraction reduces to 421 over 500. To convert to a percentage, once again, we'll just move the decimal point 2 places to the right. So 0.842 is equal to 84.2%. Whether you're converting a fraction to a decimal or a percentage, the process is largely the same. Your goal is to create a denominator of 100 without changing the value of the fraction. Let's take a look at a few examples here. Let's take 1/5. To convert the denominator to 100 without changing the value of the fraction, we have to multiply both the numerator and the denominator by the same number. The number that allows us to create a denominator of 100, in this case, is 20. So we'll multiply 1/5 by 20 over 20. 1 times 20 is 20. 5 times 20 is 100. Now once you have your number over 100, all you have to do is write the numerator as a percentage. So 20 over 100 equals 20%. To write it as a decimal, you write the numerator with a decimal point following it, 20 point, and you move the decimal point 2 places to the left because your denominator is 100. So 1, 2, there's where your decimal point will be. And we'll put a 0 in front of it so that we can recognize it as a decimal. Let's take one more example. 23 over 25. Now, to get your denominator to 100 in this case, we need to multiply on top and bottom by 4. So 23 over 25 times 4 over 4 is equal to 23 times 4 is 92. 25 times 4 is 100. So we've got it in our form we need, 92 over 100. So we can write it as a percentage, 92%, and as a decimal, 92. Move the decimal point 2 places to the left, right there, and add a 0.
Decimals. Decimals use place value to represent an amount. To read a decimal, like we have here, first read the number to the left as a whole number, followed by and, then read the number to the right of the decimal, followed by the last place value. So this number would be read as 641 and 5,129 10,000ths. This number could also be represented as a mixed number. 641 and 5,129 10,000ths. Let's look at another decimal. 5 and 8,139 10,000ths. We could write this number as an improper fraction by taking the 5 plus, this would be 8/10ths since it's in the tenths place, plus 1/100ths plus 3,000ths plus 9/10,000ths, which would give us 58,139 10,000ths. So we've seen a decimal in decimal form. We've seen it represented as a mixed number and also as an improper fraction.
Like multiplication, one of the hardest things about dividing two decimals is figuring out where the decimal point goes in the answer. But once again, I'm going to demonstrate a method that allows you to locate the decimal point before you begin. Let's look at these examples. First, we have 0.48 divided by 0.015. The first thing we're going to do is set up a long division problem using whole numbers. We're going to have 48 on the inside and 15 here on the outside. Now the decimal point is going to start here. To get to 48 from 0.48, we had to move the decimal point 2 places to the right. So we're going to move this decimal point 2 places to the left. So now we're over here. To change this to a whole number, we had to move the decimal point 3 places to the right. So we're going to move the decimal point back 3 places to the right. So that is where the decimal point in our answer is going to be. Now 15 goes into 48 3 times. So we have a 3 right here. 3 times 15 is 45. Subtracting this, we have a remainder of 3. We'll add in this 0 here. 15 goes into 30 2 times. So we have a 2 here. This is a 30 also, and we have a remainder there of 0. So this is our answer. 0.015 goes into 0.48 32 times. Let's look at the next example. Once again, we're going to convert these to whole numbers and set up long division. We have 572 on the inside and 22 on the outside. Decimal point starts here. With 572, we had to move the decimal 3 places to the right, so we'll move it 3 places to the left in the answer. And then for 2.2, we had to move the decimal point 1 place to the right, so we'll move this back 1 place to the right for the answer. So that's the location of our decimal in the answer. Now, we can do long division. 22 goes into 57 2 times. So we're going to start out with a 2 here. 2 times 22 is 44. 44 from 57 is 13. Now 13 is smaller than 22, so we have to grab this 2. 132, 22 goes into 132 6 times. So we have a 6 up here. 6 times 22 is 132. So once again, that takes care of the remainder of the number. So this is our solution, 0.26.
Exponents. Exponents or powers represent the number of times a base number is multiplied by itself. For example, 3 to the 4th power is 3 multiplied by itself 4 times because of the exponent 4, which is 3 times 3 is 9, times 3 is 27, times 3 is 81. Let's look at this set of numbers here. 2 to the 4th is 2 times itself 4 times. 2 times 2 is 4, times 2 is 8, times 2 is 16. 2 cubed, or 2 to the 3rd power, is 2 times itself 3 times. 2 times 2 is 4, times 2 is 8. 2 squared is 2 times itself 2 times. 2 times 2 is 4. 2 to the 1st power is just 2 times itself 1 time, or just 2. Now 2 to the 0. That's one that seems tricky at first. So let's look at this pattern to see if we can figure out what it would be. If you look at this set of numbers here, with each number, my exponent has been reduced 1. And it continues to be reduced by 1. And if we look at the pattern of the result, 16, 8, 4, 2, you can see that the pattern is 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. So if we continue with our pattern, if we continue dividing by 2, then the next number in our sequence, 2 divided by 2, would be 1. So 2 to the 0 power is 1. Continuing with our pattern, dividing by 2, 1 divided by 2 is the fraction 1 divided by 2. So 2 to the negative 1st power is 1/2. Continuing with our fraction, so again dividing by 2 again, 1/2 divided by 2 is 1/4. So 2 to the negative 2 power is 1/4. What you're doing with these negative exponents is that you're taking your base number to the negative exponent and you're doing the reciprocal of that. So 2 to the negative 1 is really 1 over 2 to the positive 1st power, which is 1/2. 2 to the 1st power is 2. Same thing with 2 to the negative 2 power. So again, we're going to find the reciprocal of that. 1 over 2 to the 2nd power. 2 squared is 4. So we have 1/4, which is where that number came from. Regardless of the base, it's true that a number raised to the 0 power equals 1. It'll always be 1. 5 to the 0 power is 1. 10 to the 0 power is 1. Any number to the 0 power is always 1. And a number raised to a negative power is the reciprocal or the multiplicative inverse of that number raised to its positive counterpart, like we did here. So let me show you one more example using a different number. 5 to the negative 4th power would be 1 over 5 to the 4th power. So finding that multiplicative inverse is how we get rid of that negative on our exponent, which is 1 divided by 625. Graphing solutions to linear inequalities. First, we're going to graph y is greater than 1/3 x plus 2. To graph a linear inequality, we're going to graph the line as if this were an equal sign, and then if it's greater than or less than, it's a dashed line. If it's greater than or equal to, less than or equal to, we use a solid line. So since this is just greater than, we need to use a dashed line. This is in slope-intercept form. Y equals mx plus b. So our slope is 1/3. And our y-intercept is 2. So we're going to start with our y-intercept at 2. And then use our slope to find our next point. Rise 1, run 1, 2, 3. And then we'll draw our dashed line. Connecting our 2 points. The final thing we need to do to graph an inequality is to shade. But where do we shade? One way to figure this out is to pick a point on either side of the line and see if it satisfies your inequality. If it does, then that's the side you shade. If it doesn't, then you shade the opposite side. A good point to use is 0, 0 because it's pretty easy to solve for. So y is 0. Is 0 greater than, and then again we'd plug in 0 for x, 1/3 times 0 is 0, 0 plus 2 is 2. So is 0 greater than 2? No, it isn't, which means since 0, 0 does not work, it is not a solution, then this is not the side we shade. So we shade the other side. And really everything above this would be shaded, but I'm not going to color the whole board. So this would be your solution to this inequality. Every point in this shaded region would make this inequality true. However, points on the line would not make the inequality true since its y is greater than, not greater than, or equal to. And that's why this line is dashed, to symbolize that the points that are on this line, the points that lie on this line, do not satisfy this inequality. Now we're going to graph a system of inequalities. The same rules apply, but where you shade is a little bit different. So first we're going to graph y is greater than or equal to 2x plus 3. Since it's greater than or equal to, we use a solid line. And again, it's in slope-intercept form. So our slope here is 2, or 2 over 1, and our y-intercept is 3. So we start with 3, up 1, 2, 3. And then we use our slope, rise 2, run 1. Now we can draw our solid line through these points because again it's a greater than or equal to. And there are a couple of different ways you can do the shading. One thing you could do is start by figuring out where you would shade for this line. So like again, you could use that point 0, 0. 2 times 0 is 0, 0 plus 3 is 3. Is 0 greater than or equal to 3? No, it isn't. So for this line, we'd be shading on this side of the line. And we can put like a little dot here just to remind ourselves. This is the side we'd be shading for this line. And then you can graph your other line and see where you'd shade for that one. Where they overlap is going to be the solution. And that's one way, and I'll show you another way when we're done graphing the other line. So this next line is y is less than negative 1/2 x minus 2. Less than, since it's not less than or equal to, that means we're going to be using a dashed line again. And again, it's in slope-intercept form, so our slope is negative 1/2 and our y-intercept is negative 2. So start with the y-intercept, negative 2, and then use your slope to find your next point. Rise 1, or actually we're going down 1 since it's a negative 1, and then over 2. And again, this is a dashed line because it's just less than, not less than or equal to. We're going to connect our points with our dashed line. And put our arrows on the end to signify that that line goes on. So now that we have our two lines crossing, we've actually created 4 regions. We have this region, this one, and this one. For our first line, this region was what was shaded. So now we need to see where we're shading for our next line. Is it above the line or below this dashed line? Again, I'm just going to use 0, 0 in order to check. So negative 1/2 times 0 is 0. 0 minus 2 is negative 2. So is 0 less than negative 2? It is not. So this is not where we're shading for this one. We're shading down here in this region. And so where the two shaded areas overlap would be right over here. This is your solution, since for this line we were shading on this side, and for this line we were shading on this side. So the two shaded areas that overlap is just this region right here. And another way you could figure this out is just to pick a point in all 4 of the regions. And if the point satisfies both equations, then that's where you shade. And if your point doesn't satisfy both equations, then we don't shade in that region. Multiplying decimals. When multiplying decimals, instead of lining up the decimal point, we line up the last digits on the right. So if we were multiplying 4 and 23/100ths times 9 and 75,000ths, we'd want to line up our last digits. So 3 is the last digit in 4 and 23/100ths, and 5 is the last digit in 9 and 75,000ths. There's my 7, my 0, my decimal, and 9. Now we multiply just like we multiply whole numbers. So starting with 5, 5 times 3 is 15, carry the 1. 5 times 2 is 10, plus 1 is 11, carry the 1. 5 times 4 is 20, plus 1 is 21. And then I'll get rid of these. For our next number, now that we're multiplying times the 7, we need a 0 placeholder. 7 times 3 is 21. Write your 1, carry your 2. 7 times 2 is 14, plus 2 is 16. Write your 6, carry your 1. 7 times 4 is 28, plus 1 is 29. Get rid of those. Then we need 2 zeros for placeholders. And when we multiply times 0, 0 times 3 is 0, 0 times 2 is 0, and 0 times 4 is 0. We just get a line of zeros. So moving on to our last digit, now we need 3 0 placeholders before we multiply times 9. 9 times 3 is 27. Write the 7, carry the 2. 9 times 2 is 18. Plus 2 is 20. Write the 0, carry the 2. 9 times 4 is 36. Plus 2 is 38. Then just like we would with any other whole numbers, we're going to add our results together. 5 plus all these zeros gives us 5. 1 plus 1 is 2. 1 plus 6 is 7. 2 plus 9 is 11. Plus 7 is 18. Write our 8. Carry our 1. 1 plus 2 is 3. And then we have 8 and our 3. To determine where the decimal point goes when you've multiplied your decimals together, we're going to take how many numbers there were behind our decimal in our first number and how many numbers there were behind our decimal in our second number and add those together. So since we had 2 numbers behind the decimal here and 3 numbers behind the decimal here, then our result will have 5 numbers behind the decimal. 2 plus 3 is 5. 1, 2, 3, 4, 5. So this is the result of multiplying my 2 decimals together. Order of operations. Before simplifying expressions, it is important to know which operations to perform first if more than one operation is present in the expression. Please excuse my dear Aunt Sally, or PEMDAS, is often used for remembering the order of operations. P is for parentheses. Anything in parentheses should be done first. This one's a little misleading though, because it's not just parentheses that should be done first, it's all grouping symbols. Brackets, absolute value, anything that groups numbers together. Followed by exponents, and then their inverses, roots, should be done next. Following that is multiplication and division. And this is special because multiplication and division, it's not that one needs to be done before the other. These are just worked from left to right. So in your expression, when you're looking from left to right, you'll do all your multiplication before you do your division. Finally, addition and subtraction work the same way as multiplication and division. So these will also be done from left to right, but these will be the last things done when simplifying an expression. Let's put PEMDAS to work. We're going to simplify this expression. So according to PEMDAS, we need to start with our parentheses or our grouping symbols. 3 plus 9 then is where we need to start. That's the only thing we're going to simplify, so everything else stays the same. 2 plus 5 minus 3 plus 9 is 12. Divided by 2 squared. We're done with our parentheses or grouping symbols, so next up is exponents. And we have an exponent right here at the end, so 2 squared will be the next thing we simplify. 2 plus 5 minus 12 divided by 2 squared means 2 times itself 2 times, which is 4. Then we have our multiplication and division from left to right. So as I look from left to right, all I have is this one division operation to perform. So that'll be the next thing we do. 2 plus 5 minus 12 divided by 4 is 3. Finally, we get to our addition and subtraction. Again, these are worked from left to right. So 2 plus 5 is 7. Bring down our minus 3, and 7 minus 3 is 4. So this expression, simplified, would give you 4. Now let's see what happens if we ignore the order of operations and just work from left to right. If we were just working from left to right, we would start with 2 plus 5, which would give us 7, minus 3 plus 9 divided by 2 squared. Then we would do our 3 plus 9, so we'd have 7 minus 12 divided by 2 squared. 7 minus 12 would give us negative 5, since we can add the inverse. 7 plus negative 12, negative 5, divided by 2 squared. Negative 5 divided by 4 is negative 5/4. So as you can see, if we ignore the order of operations, we get a completely different answer, which is why it's very important to make sure you're always going in the correct order whenever you solve or simplify an expression. Percentages. Percentages are values that are used to compare numbers to 100. All percentages equal the number divided by 100. For example, 35% means 35 out of 100. So you could express it as 35 out of 100, which could then be simplified to 7/20. You could also write 35 out of 100 as a decimal 35/100. So percentages, again, are just that number out of 100. Let's take 85%. 85% means 85 out of 100, which can also be simplified to 17/20. And 85/100 can be written as a decimal 85/100.
It's very important to understand place value. So consider the number 14,059. You need to be able to look at this number and look at each individual digit and know whether it's representative of the 10,000s, the thousands, the hundreds, the tens, or the ones. So starting out with 9, 9 right there is representative of the ones because we know we have 9 of something. If you just saw the number 9, like 9 turtles, you know 9 is in the ones place because we're just talking about 9 turtles. Now when you get to the tens place, the 5 here is representative of the tens place. Because if you saw the number 50, the 5 right here means there's 5 tens. In other words, there's 10 plus 10 plus 10 plus 10 plus one more 10. See, there's 5 tens here added together. So the 5 is in the tens place. And so as you just progress to the left, you're able to name each one. So we get to the hundreds place. In this case, that's 0. So the next one's going to be 4, which is in the thousands place. And then 1, which is in the 10,000s place. And so as you continue, if you want one more, then you would have the 100,000s place, and so on and so forth. So just remember, when looking at a number, start all the way at the right with the ones place and work to your left to name the place value of each digit in that number.
Proportions and percents. Proportions can be very helpful in solving problems dealing with percents. Let's look at this problem. Suppose a pair of shoes is on sale for 20% off of the original price. If the original price is $85, how much money will you save? Keep in mind that a percent is a part out of a whole. And that whole is 100 when you're dealing with a percent. So 20% off, that would be 20 out of 100. And now we've set up our first ratio. And the key with proportions is to be consistent with your ratios. So since our first ratio is the part out of the whole, then our second ratio also needs to be the part out of the whole. The whole in this case being your price. That's the total cost, so that's your whole. That's your denominator, 85. And then the how much money you save is going to be your part, because you're only going to save part of the whole. And since that's what we're trying to find, how much money will you save, that's going to be our variable. So we can just use an x or anything. And then to solve our proportion, we're going to cross multiply. So we cross multiply 100 times x, which is 100x, is equal to 20 times 85. 2 times 85 is 170, and then we add a 0 for the 20, so 1700. Then to solve for x, we have 100 times x, and the opposite of multiplying is dividing. So we divide both sides by 100. 100 divided by 100 is 1 times x is x. Cancel our two zeros. 17 divided by 1 is 17. Therefore, if our $85 pair of shoes was 20% off, then we'd be saving $17 when we buy our shoes. Ratios. A ratio is a comparison between two quantities. You can think of a ratio like a fraction. And since it's just like a fraction, a comparison of two numbers, it is treated a lot like a fraction, meaning you're going to simplify it anytime you can. Let's look at this problem. Suppose a sampling of fish from a local pond contains 12 bass, 8 catfish, 38 minnows, and 4 trout. What is the ratio, so the comparison of two numbers, of bass to minnows? Now, when they ask you this question, they're telling you exactly how to set your ratio up. Since it says bass to minnows, we read left to right. We also read from top to bottom. Since a ratio is a fraction, then they're telling you what your numerator should be and what your denominator should be. So our ratio is going to be bass to minnows. And now we can substitute how many bass and minnows we have. According to our problem, we have 12 bass and we have 38 minnows. So that ratio would be 12 to 38. But again, since this is a fraction, we're going to simplify it if we can. And 12 and 38 do have a GCF of 2, so we're going to divide 12 by 2 to get 6, and we'll divide 38 by 2 to get 19. Therefore, our ratio of bass to minnows is 6 to 19. But that's not the only way we can write a ratio. We could also write it as 6 to 19, or as 6 to 19. And these all mean the same thing, and they all give you the same information, that for every 6 bass in the pond, there are 19 minnows in your pond. It is important, though, the order of your numbers. Since the ratio they were asking for was bass to minnows, your bass number should be first, and then your minnows number. So make sure you put it in the right order. That is very important. Rounding. Rounding involves increasing or decreasing a number to a specified degree, which makes calculations easier to perform, and it helps to communicate the important aspects of a number. Usually, the directions will read to round up, round down, or simply to round, followed by to the nearest, and then you'll be told to round to the nearest hundreds place, tens place, whole number, tenths, hundredths, etc. If the directions say simply to round, then you'll look at the digit to the right of the place you're rounding to. And if that digit is from 0 to 4, then that number stays the same. And if the digit is 5 through 9, then you round up. Let's look at rounding 271 and 459 thousandths to the nearest hundred first. So if we're rounding to the nearest hundred, then we're trying to round to this place. 2 is in the hundreds place. Therefore, we need to look at the digit to the right, which is 7. And since 7 is greater than 5, then we have to round up to 300. Next, we're going to round the same number to the tens place. So the 7 is in the tens place, and we're going to look to the number to the right of that, which is 1. And since 1 is less than 5, then we're going to stay the same. So this would be 270. Next, we're going to round to the whole number place. So we look at 1, it's in the whole number place. The digit to the right of that is a 4. Since 4 is less than 5, then our number stays the same at 271. If we are rounding to the tenths place, 4 is in the tenths place, so we look to the right, and the 5 is 5 or greater. Therefore, we need to round our number up, so the 4 is going to go up to a 5. So that would be 271 and 5/10. The last place we're going to round to is the hundredths place. So we're rounding to the hundredths place, which is right here where the 5 is. So we look at the digit to the right, which is 9. And since 9 is greater than 5, we're going to round 5 up to 6. So that's 271 and 46 hundredths. Now we're going to look at an example of rounding up instead of just rounding. We're going to round the number 6001 up to the nearest. First, we're going to round it up to the nearest 10,000. So the nearest 10,000 that's greater than 6001 would be 10,000. To the nearest 1,000, we're rounding up to the nearest 1,000. So the nearest 1,000 number that's up above 6001 would be 7,000. We're going to round up to the number that's to the nearest 100 place. So the next number above 6001 to the nearest 100 would be 6,100. Since 100 is the first 100 you would come to. Finally, we're going to round 6001 up to the nearest tens place. So the next nearest number, or the next nearest 10 from 6001 would be 6,010. Multiples. You can think of multiples as like counting by that number. So for instance, the multiples of 2 would be 2, 4, 6, 8, 10, etc. The multiples of 3 would be 3, 6, 9, 12, 15, 18, etc. The multiples of 4 would be 4, 8, 12, 16, 20, and so on. Sometimes you're asked to find the LCM of 2 or more numbers. The LCM is the least common multiple. Least meaning the smallest, common meaning the same, and multiple. So if we wanted to find the LCM of, let's say, 2 and 3, the least common multiple of 2 and 3, so the smallest number that 2 and 3 have in common, would be 6. So that's the LCM of 2 and 3. The LCM of, say, 3 and 4, the very smallest number that they have in common would be 12. And you can find the least common multiple of bigger numbers, like, say, the least common multiple of 12 and 15. So 12 would be 12, 24, 36, 48, 60, 72, etc. While 15 would be 15, 30, 45, 60. Oh, so if we were finding the LCM of 12 and 15, the smallest number they have in common is 60. So the least common multiple is 60. Numbers and their classifications. First, we have integers. Integers are the set of positive and negative numbers, including 0, which is neither positive nor negative. But integers do not include numbers like fractions or decimals. That means no mixed numbers either. So integers would only be numbers like negative 100 or positive 7 or negative 15 or positive 2. Just no fractions, no decimals, but we can have positive and negative numbers, and it also includes 0. Next, we have even numbers. An even number is any integer. So remember, by saying it's an integer, we're already not including fractions and decimals. So it's any integer, no fractions or decimals, that can be divided by 2 without leaving a remainder, which means we can divide it evenly. So an example of an even number would be 2, 4, 6, 8, 10, 12, 14, 16, etc., etc., etc. We could go on forever naming even numbers. Next, we have odd numbers. An odd number is, again, any integer, so no fractions or decimals, only positive and negative numbers including 0, that cannot be divided evenly by 2. So the exact opposite of an even number. Even numbers can be divided by 2 evenly, and odd numbers cannot be divided evenly by 2. And so an example of those numbers would be numbers like 3, 5, 7, 9, 11, 13, 15, 17, 19, etc., etc., etc. A decimal number is a number that uses a decimal point to show the part of the number that is less than 1. For example, in the number 1 and 256 thousandths, we use this decimal point to show this part that is less than 1, rather than using a fraction. And so then we get to decimal point. A decimal point is a symbol used to separate the ones place from the tenths place, like we did in this number right above us. this decimal point separates our ones place from our tenths place. So it shows you which part of the number is 1 or greater and which part of the number is less than 1. Finally, decimal place. That's the position of a number to the right of the decimal point. So in this number, 0 and 123 thousandths, the 1 is in the first position to the right of the decimal, and so that's the tenths place. The 2 is in the second place to the right of the decimal, that's the hundredths place. And the 3 is in the third position to the right of the decimal, that's the thousandths place. And it continues on like that. Tenths, hundredths, thousandths. Next would be 10 thousandths, 100 thousandths, and so on and so forth. Notice that they all end in a THS. So it's not 10,000, it's 10 thousandths because it's decimals. So what our whole system is based on is the base 10 system. We have 10 different digits to work with, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we can arrange those numbers in lots of different ways that mean lots of different things. But of course there are other systems besides the base 10 system, like the binary system. And that's what computers use. And the binary system, that prefix bi means 2. So in the binary system, they only use 2 numbers, 0 and 1. And they put those numbers together to mean different things as well. It's thought that maybe we use the base 10 system because we have 10 fingers and maybe 10 toes, so it was just easier to come up with something like the base 10 system. But these are our numbers and what these different words mean. Parentheses. Parentheses are used to designate which operations, which is addition, subtraction, multiplication, division, should be done first when there are multiple, so more than one, operations. For example, 4 minus the quantity 2 plus 1. Since 2 plus 1 is inside the parentheses, we must perform that operation first. We must add 2 plus 1 first. So 4 minus 3, which yields 1. If we had not added 2 plus 1 first, then 4 minus 2 would be 2, plus 1 would give us 3. So there would be a different answer. So that's why we need to know that parentheses mean that we do that operation first.
Work. Work is the amount of energy expended in accomplishing a goal. The simplest equation for work is W equals FD, which means F times D, and that is where F is the amount of force exerted and D is the displacement of the object upon which force is exerted. So, work is going to equal the force times the displacement, how far the object moved. This equation requires that the force be applied in the same direction as the displacement. If force is exerted in the same direction, then this formula will work. If force is applied in a different direction, you might have to alter your formula. So, if we had this boulder and force was exerted forward and the boulder moved forward and was displaced this distance, we could say work equals the force used to push the boulder times its displacement. because force and displacement went in the same direction. Now, if this is not the case, work may be calculated a different way. It can be calculated using the formula W equals FD cosine of theta, which means force exerted times the displacement times the cosine of theta, where theta is the angle between the force and displacement vectors. So, the angle between the direction force was going and the direction the displacement actually went. So, let's look at our boulder again. Let's say we pushed at this angle and the boulder moved forward along the ground. Well, this angle between the displacement vector and the force vector would be theta, and we would plug that into our formula to figure out the actual work done. Now, if force and displacement have the same direction, work is positive. So this would be an example of positive work. If force and displacement have opposite directions, work is negative. So an example of that would be if someone were over here, if we had the same displacement, but some person was over here and they had a lever system, like a lever and pulley system going, and they were able to pull the boulder toward them. So if they were able to pull the boulder toward them, they would be exerting force from over here, but they would still be displacing the boulder this way. So if they were exerting force this way while displacing this way, the work would be negative. So force going to the left, displacement actually going to the right, that would be negative work. And if force and displacement directions are perpendicular, work is 0. So the work done would equal 0. And that means no work is done. An example of that would be the ground pushing up on the boulder. The ground has its own force pushing up on the boulder. If the boulder is moved to the right, the ground's force against the boulder did not affect the displacement, and so no work was done by this force. So even though the boulder moved from here to here, the ground remained pushing up against the boulder, and no work was actually done by this force. Work is measured in joules, and a joule is the work expended by a force of 1 Newton through a distance of 1 meter. So if you exert 1 Newton of force through a distance of 1 meter while you're pushing an object 1 meter, that is equal to 1 joule, and work is measured in joules. So when you're multiplying and using this formula, force is going to be measured in newtons. Your displacement should be measured in meters. So if you need to translate between different units to get your force to newtons and your displacement to meters, then please do so. And then you will get a joule or number of joules as your answer for how much work was expended.